other. And here we go. Hello and welcome back to Calculus 1, section 2.6, continuity part 1, because we don't have time to finish everything. There will be part 2 tomorrow. Continuity. The most basic idea, which is not entirely true, is that the function is continuous if you can draw its graph, in one stroke. You don't get to lift the pen off the paper. So that's the most primitive way to say. There are some advanced functions that are continuous, but the way you graph them, you have to lift the pen because it's constructed from segments. These functions are in advanced calculus, and they consist of little segments, so you would have to draw a segment over here, then you draw a segment over here. Then you draw a segment here, and then a segment, and then another segment, and another segment. So you see that it's a continuous line, but the way you draw that line was not this, right? So in the future, there are going to be functions that are continuous, and you can't draw them, in a single stroke. But for the most part, all of the functions that we are going to discuss in calculus, that includes 1, 2, and 3, are going to be, it's continuous, and you can draw it in once, like, x cubed. Well, x cubed this way, or x squared, or e to the x, or ln x, or absolute value of x, right? So all of them are continuous. So continuity for a function means that there are no interruptions, there are no breaks, there are no jumps. So something like this, if you look at it, you would say it's continuous. Something like this, with a jump, or something like this, we would say discontinuous. Now, please observe that these discontinuities happen at the point, at the particular location, call that location A, on x-axis, right? So it makes sense first to define continuity at the point, continuity at a single point, and then define global continuity afterwards, and then follow with a whole bunch of theorems that will ease up our calculations. So that's the roadmap of the whole lecture. So we start with the definition, continuity at a point. Function f of x is continuous at x equals a if, and now we have 3 conditions that function has to meet in order to be continuous at point A. First condition is that f of a must exist. Which means y value, right? Y value at A has to exist. Observe. Does not exist there, right? So it's discontinuous. Number 2, limit f of x as x goes to a must exist. And number 3, 1 has to be equal to 2. So limit of f of x has to be equal to f of a, right, in order for this. So this is the definition of the continuity at a point. And now we're going to draw some pictures. We're going to go back to those. You remember those 4 pictures we had? So I'm going to draw 3 of those 4 now. Well, actually, no, all 4, but 1 is continuous, everything, so we don't have to consider that case. So let's take a look at the first example. This is the most basic, fundamental idea you can possibly imagine. So is f of x equal x squared minus 3 continuous at x equals 5? That's your question, right? All right, well, let's figure it out. First thing from our list is we have to be able to compute at 5. So can I find f of 5? Well, yeah, that's 5 squared minus 3, which is 22. Great. We got it. Number 2 says, how about the limit of x squared minus 3 as x goes to 5? Well, now you go back to 2.3 or whatever you have to go back to compute that limit, and the answer is yes, it exists, it's 22. And now number 3, 22 equals to 22. It passed all 3. So what is the answer? You can't just, write this and walk away. You actually have to give the answer. Answer is yes. F of x, x squared minus 3, is continuous at x equals 5. And that's your answer. So this green sentence is your answer. You have your partial credit for calculating 1, 2, and 3, but then your final 2 points are where the green stuff is, because that is the answer to the question. The question says, is x squared minus 3 continuous at 5? What kind of answer is 22? That makes no sense as the answer, right? So you can't leave this stuff as the answer. That makes no sense. You have to provide the proper answer for it. Okay, good. So that's the idea. Now, replace that x squared minus 3 with e to the x squared, with sine x, with 1 over x squared plus 2. Again, I can't do every single function, the square root function, the rational function, the exponential function, the logarithmic function, right? We'll be staying with each calculus concept just an hour for me to do every function you learned so far, right? So it applies to a function. You better be able to compute with those functions from your previous math experience. So that's that part. And then what else do I have? So that's that. So now we understand continuity at the point. Now, what does it mean to be discontinuous? Well, clearly, in that case, one of these 3 fails. And I'm going to draw 3 graphs and ask you to try and tell me which of the 3 rules fails on these graphs. Now, I have to repeat those rules here. So f of a exists. Number 2, limit f of x exists as x goes to a. And number 3, limit f of x is equal to f of a. So 2 is equal to 3, technically. Sorry, 1 is equal to 2. So these are the 3 rules. So the first graph is this one. Second graph is this one. And the third graph is that one. You look at these and you know they're all discontinuous, which means that something out of this list, 1, 2, 3, fails. What fails on the first graph? Which rule? Rule 3. Rule 2, limit does not exist. Look at the limit from the left, is the top point. Limit from the right is the bottom point. So, rule 1 passes because it's right here. That's where the black point is, right? The filled-in dot, that's where the function value f of a is. So, rule 1 passes, rule 2 fails, and we are out, right? So, we don't check rule 3 in that case because you can't even check because one of the 2 rules didn't pass. How about the second graph? What fails on the second graph? Rule 3. Rule 3. So 1 passes because that's again where the filled-in dot is, right? The black dot. That's where we have f of a. So it exists. Open circle is where the limit is. That exists as well. And then they are not at the same y. They're not at the same y value, which means third rule fails there. And now by process of elimination, right, on the third graph, first rule fails immediately because there is no f of a. There is no function value. Remember, if I try to compute value a, it's just going to shoot through the point and never return the y value. So that's why the first rule fails. So the first one is called jump discontinuity. There is that's words that you might want to know. I don't know. Great. Now we discussed the idea of continuity and discontinuous. Now we need to be well, let's do the global continuity now. No, global continuity after the this other. If I do global, let's do global. It's just because some of you are writing with pens, so when I said no, you scratched it off, and now when I say yes, you have to write it again. That's the only reason. Global continuity. Definition, right? If f of x is continuous at each of the points in its domain, we say that f of x is globally continuous. So The first definition said that this x squared minus 3 is continuous at 5. But then what's happening at 5.37? What's happening at negative 1.3? Right? You have to redo this calculation for every single individual point that is given to you. Right? And when you do all of those calculations, which is infinitely many, at which point now you're elves, right? Because you have to live forever. Then the function is globally continuous. So you see, it's a little bit difficult to compute that, right? So we'll put some theorems in place. But before we go and look at those theorems, I have another thing that will make this story more interesting. Function is continuous at the point. Function is globally continuous. Function is discontinuous. But then, function is piecewise continuous as well. Let me give you an example. We can go and test, let's say, 1 over x. F of x equals 1 over x. We know, because we look at it and see, there is a vertical asymptote at 0. So, vertical asymptote at x equals 0. That immediately means that 1 over x is discontinuous. But that's globally. It's globally discontinuous. But I have two pieces that are continuous, right? So what is now the piecewise continuity? Piecewise continuity means that the function is continuous from negative infinity to 0, not including, right? And on 0 to infinity. So if I am to erase half of the graph, I have perfectly continuous graph, right? Now if I am to add that half back, oh really? If I am to add that half back, now globally function is discontinuous, but the two pieces are what we say piecewise continuous. This is going to be very important for your Calculus 2 if you are going to Calculus 2. Some of the problems in Calculus 2 are very interesting. Should I say very interesting? Do I have Calculus 2 on this one? Calc 1, Calc 3, Calc 1, Calc 3. How about here? Calc 1, Calc 3, no. Too bad. Wanted to show you the problems from Calc 2. These types of continuity proofs and theorems and things pop up in that course a lot. And piecewise continuity is important in certain proofs that you will be working on in chapter 8. So this is important. All right, so the last piece for today, and we'll do the second portion tomorrow of this, obviously many more examples and things, is to write the theorem of which functions are globally continuous. That's important because you don't get to test every single point to show that continuity point by point, because there are infinitely many points. So, following functions are globally continuous. Number one, linear function. I don't like that it's singled out because it's the part of polynomials. So polynomials. Globally continuous on the entire domain. That's important. On the entire domain. So linear function, polynomial function, linear is a part of that, and quadratic and constant function, they're all in that. 3. Radical function. 4. So we have radical function, then 4 sine x, cosine x, not the other ones. Exponential function. Logarithmic function. Now, rational function, which divides two polynomials, can very easily be discontinuous, right? As soon as the denominator is equal to 0, it's either open circle or a vertical asymptote. Now, sure, if you have your denominator to be x squared plus 1, right? Well, then there's no way to make 0. Yes, but this situation, that the exotic situations, will be covered in the next theorem, which we are going to cover tomorrow, on combining continuous functions. So that's going to be addressed later. But these are the basic functions that you are dealing with, and all of these functions. Now you also have inverse trig. Because the inverse trig functions are all continuous because they're very small pieces that are continuous. That's on the list as well.
So is tangent inverse not continuous?
No, right? Because it's you have all those vertical asymptotes at pi over 2, 3 pi over 2, 5 pi over 2, and then the cube-like squiggle in between, right? So tangent x is not continuous. It's piecewise continuous with infinitely many vertical asymptotes. Tangent is an example. I forgot to mention that. So generally you have 1 or 2 vertical asymptotes per problem in Calculus 1, and then you hit tangent and secant and cosecant and cotangent, and all of them have infinitely many vertical asymptotes because they're periodic functions. They repeat, and if you're going to infinity, yeah, you're going to have infinitely many asymptotes. So that's one of the cool parts. Good. All right, so that's that for today. Part 2 tomorrow. We are going to do some combinations of these functions and so on. So more fun tomorrow.